Hi, I am Sukirti KV, first year MSc Biochemistry, JSS SLS Mysuru. In this presentation, I am going to explain about the chymotrypsin. First, we see the introduction of the chymotrypsin. Chymotrypsin is an enzyme used for digesting the proteins. Chymotrypsin is also found in the duodenum that selectively cuts the pieces of the amino acids from the protein chain. Specifically, chymotrypsin cleaves the phenylalanine, tyrosine, and tryptophan bonds, or in the other words, the aromatic amino acids. It cleaves these amino acids starting from the C terminus of the protein. Now we see the chymotrypsin structure. The primary structure shows that sulfide bonds are the crucial role to the protein folding. The protein is spherical and itself consists of the three polypeptide chains. There is also a pocket in the enzyme other than the active site and known as S1 pocket, which in the case of chymotrypsin is lined with the relatively hydrophobic residues such as serine 189, serine 214, serine 215, glycine 216, glycine 226. The active site includes serine 195, histidine 57, and ASP 102. Serine 195 is hydrogen bonded to the histidine 57, and it in turn is the hydrogen bonded to the ASP 102 residues. The histidine 57 role is to position the serine residues and polarize the hydroxyl group so it can be deprotonated to the alkoxide ion. In the presence of the substrate, this accepts a proton by acting as a base. And this is the chymotrypsin structure which is in the form of folding. Now we see the mechanism of the action. In the step 1, when substrate, that means polypeptide bonds, the sides of the chain of the residue next to the peptide bond to be cleaved nestles in a hydrophobic pocket on the enzyme, positioning the peptide bond for attack. Histidine extracts one proton from serine to form an alkoxide ion. This serine ion reacts with the substrate. In the second step, in the chymotrypsin, the carboxylate R group of ASP 102 forms a hydrogen bond with R group of histidine 57. When this happens, it compresses this hydrogen and shifts electron density to the nitrogen bond, not involved in the H group. In the R group of histidine 57 becomes a very strong base. This allows the histidine 57 to deprotonate serine 195 and turn it into a strong nucleophile that can attack the substrate. In the step 3, instability of the negative charge on the substrate carbonyl oxygen when will leads to collapse of the tetrahedral intermediate, reformation of a double bond with carbon which breaks the peptide bond between the carbon and amino acid group. The amino leaving group is protonated by the histidine 57, facilitating its displacement. Once the oxygen hole stabilizes the negative charge, the bond breaks because the proton from histidine is binding to nitrogen to make it less likely to carbon. The leaving group is stabilized and the acyl enzyme is formed. In the step 4, the amine component is departed from the enzyme, metabolized by the body, and binds to serine. This completes the first stage, that means acylation of enzyme. The first product was being made. In step 5, a water molecule is added where the N terminus was histidine protonated the water to form a hydroxyl group. This hydroxyl group attacks to carbon from the carboxyl side and destabilizes the acyl intermediate. The bond is broken. In step 6, an incoming water molecule is deprotonated by acid-base catalysis, gene generating a strongly nucleophilic hydroxide ion. Attack of hydroxide on the ester linkage of the acyl enzyme generates second tetrahedral intermediate. In step 7, collapse of the tetrahedral intermediate from the second product, a carboxylate anion and displace serine 195. The proton from histidine goes back to the serine. In step 8, the carboxylic acid is released and the enzyme is reformed to catalyze the next reaction with the original active site. And this is shown in the schematic representation how the mechanism acts. And this is how chymotrypsin catalyzes. Thank you.